Okay, so all right. So in this lecture, let me first review the different element coordinate systems that we looked at. Okay, and then we're going to move on to the to start looking at the structure level. Okay, basically we're going to start putting our elements together. All right. So you've seen the basic system. Okay, where the basic force, F over bar prime under bar, meaning a vector, equals to the basic stiffness times the basic displacement. Okay. Basic displacement. Okay, and recall the basic displacement is the degree to which the element elongates or shortens. Okay. This is a basic force. For a truss element, this is every object here is one by one, either a vector or a matrix, but we still use matrix and vector notation because they're used in matrix operations. Okay. Right. Next thing we covered are the local element coordinates. Okay. And in that case, right, we looked at an element that's oriented in space in an arbitrary fashion. It has its starting node and end node. I is starting, J is end node. Okay. The coordinate axes are oriented such that the x-axis points along the element axis and the y-axis points in the perpendicular direction. Okay. And then we defined displacements and forces that have components in this coordinate system. Okay. So this was our delta prime 1. This was our delta prime 2, right? It's the x displacement at the start node, where x is aligned with the axis of the structural member, right? This becomes our delta prime 3. This becomes our delta prime 4, right? And then we have the corresponding forces. F prime 1, F prime 2, F prime 3, F prime 4, okay? Where prime designates local element coordinate system, right? And in that system, we derived the following equation. F prime equals K prime delta prime, like this, okay? Where delta prime is the vector of displacements in the local coordinate system. Okay. F is a vector of forces, also in the local coordinate system. Okay. And kappa prime is the element stiffness matrix. In the local coordinate system. Okay. And then finally, we went to the global coordinate system for the element. Okay. Where the element may be oriented in space in an arbitrary fashion, but it has, again, end node, start node, and then the whole element is embedded into a fixed coordinate system, xy, like this. Okay? And then the components of displacements and forces are defined along the coordinate directions x and y. Okay? That's the difference. F3, and then delta 4, F4, like this. Okay? And as before, the force displacement relationship holds through the stiffness matrix. That looks like this, okay? And K is the element stiffness matrix. In global coordinates. And so now the matrices are related through the following transformations. Okay? I can start by writing down a stiffness matrix in the basic system. Okay? I can apply gamma RBM and gamma RBM transpose, right? Remember a matrix that sort of strips away rigid body modes. This gives me kappa prime, right? Element stiffness matrix in local coordinates. And if I further multiply out by gamma ROT transpose, okay, this gives me the element stiffness matrix in the global coordinate system, right? So this is the this is a structure, and sort of it's a typical structure when you're relating one vector to another, right? Through multiplication by a matrix, like in this case, and then the various transformations, right? If the vectors transform in a certain way, that induces a transformation on the matrix, which typically involves pre and post multiplication by the transformation matrix, and this is what you're seeing here. Okay. All right. Now we'll come back to that, but let's go to the structure level. Okay. And let's start sort of chipping away at the concept of a structure stiffness matrix. Okay. And for these purposes, right, if you follow page 215, the notes define an example. Okay. It's a very simple structure, right, but reflects everything you. Let's put it this way: it's enough to introduce the basic concepts. Okay. So we have a structure like this. These ends are pinned. Okay. Meet here. This node is denoted by 1. This node is denoted by 2. This node here is denoted by 3. Okay. The structure is embedded into a global XY coordinate system, right? As I said, now, as you can imagine, the first element, we're going to call it A, right, induces its own local coordinate system, where little x is lined up with A. In fact, it is coincident with the global, right? If you look at element B, okay, has its own coordinate system. Okay? And so while at the element level, it's possible to define a local coordinate system, for the structure, you don't do that, right? As I mentioned before, at the structure level, it lives in a global coordinates. And so whatever solutions that we produce will be the solutions that are referred to the big XY coordinate system. Okay? All right, so we label the nodes 1, 2, and 3. We label the elements A and B. Okay? Let's put some dimensions. Okay? Supposedly this guy is 8 units long in this direction and 6 units long in this direction. Okay? These are units of length, right? It doesn't matter what those are. Let's just keep things numerical. Okay? In addition, we're going to apply a load here, P, and that load will have 9 units of force and will be acting downward. Okay, in addition, right, we're going to assume that element A has a stiffness E A over L of 300, the basic stiffness, and we're going to assume that element B also has basic stiffness E A over L equals 300. Okay, the numbers at this stage don't matter so much. We're going to learn some concepts. Yeah. So what's the first step? Okay, the first step is the bookkeeping step. Right? before you launch into the analysis of the structure, right, and see, let's say, what the deflections are under this loading situation, you need to write down all the information you know. Okay? And this means stating everything you know about each element. So let's start with A. Okay. All right. Well, we need to define the element orientation, meaning what's its start node, what's its end node. Okay, it's 2D, very simple. Let's just go from left to right like this. And likewise, we're going to define the same thing for B. Okay, so what that does, right, it says that node I must be node 1, and node J for element A must be node 2, like this, right? The element points from 1 to 2. Okay. Once you know what those are, you can actually compute the relevant relative coordinates, I guess, right? Relative lengths of the element in the x and y direction. It's x at j minus x at I, okay? Which is x of coordinate 1, x of coordinate 2 minus x of coordinate 1. Okay? If we look at the figure here, the distance is clearly 8. Okay? The change in the y-coordinate is computed analogously, but instead of x's, we use the y-coordinates, y at j minus y at I, same as y at 2 minus y at 1 equals 2. If we look at the picture, for element A, there is no change in the y-coordinates, so it's 0. Okay. Okay. From here, we compute L, delta x squared plus delta y squared square root, and we get 8, obviously, delta y doesn't contribute. And finally, in order to populate the rotation matrix, you need to compute the cosine phi, you need to compute sine phi. Okay, and remember, these, you don't want to try to find the angle first and then take its cosine. Take its cosine. You use the definition of a cosine, right? It's delta x over L, okay? And that definition remains true, independent of the orientation of the bar, okay? So in this case, it's 8 over 10, or 0.8. Okay? Sine phi is always delta y over L. 0 over 10 equals, 8 over 8 equals 1. Sine 0 over 8 equals to 0. Okay, so you use these. So always use this definition, okay, and it basically, you need those to populate gamma ROT matrix for a given element. Okay. And finally, as we stated, basic stiffness, EA over L, right? L is given, A and E are chosen such that the result is 300. Okay. Quickly, let's go through element B. Element B. So what do we know here, right? Again, we'll look at the orientation in the figure. Okay, it goes from 3 to 2. So node I, starting node is node 3. Node J becomes node 2. Okay. Delta x equals x j minus xi equals 2. Right, again, we'll look at the x coordinate at 2, subtract x coordinate at 3, clearly get an 8. Delta y is yj minus yi. Right, we'll look at the y coordinate here minus y coordinate there, clearly see a 6. Okay, we compute the length, delta x squared plus delta y squared. See, the numbers are chosen quite nicely. You get exactly 10. And then the sine and cosine become 8 over 10, or 0.8, and 6 over 10, or 0.6. Okay? And again, these are the entries that are used to populate the rotation matrix. Finally, basic stiffness, E and A are selected such that the basic stiffness is 300 in this case. So this is as much bookkeeping as you can do at this point, right? Actually not, right? There's the next step. It's very important. And you need to number the structural degree of freedom. Okay? So structure, DOF numbering. Okay. All right. So here, let's write sort of an abstract view. Okay. We have our element A, element B, node 1, node 2, node 3. Okay, these guys are numbers for us a priori, right? And we also know that here we have a pin, and here we have a pin. Okay, so it means that node 1 and node 3 cannot move neither in x nor in y direction. Okay, so node 2 is a free node. And 1 and 3 are restrained nodes. Okay, and so this has an effect on how the degrees of freedom are numbered, right? And so then, in principle, each node can move in x and in y direction, right? So because you have 3 nodes, in principle, you can have 6 displacements for this problem, right? So how do we number those? Okay, well, let's go to the first node, right? First node is restrained in both x and y, so it doesn't have any free degrees of freedom. Can't move. Okay, I go to node 2. This guy is completely free to move, whichever way it likes, and depending on the force, right? And so then I say, okay, the displacement in x of node 2 is going to be my global degree of freedom 1. I'm going to call it U1. And displacement in y is going to be a global degree of freedom 2. I'm going to call it U2. Okay, I go to node 3. No free degrees of freedom there. It's restrained. Okay. Once we're done numbering the free degrees of freedom, let's number the restrained degrees of freedom. Okay. So then node 1 will have U3 and U4 associated with it as x and y displacements respectively. And node 3 will have U5 and U6 associated with it as x and y displacements respectively. Okay. And so then we can define 2 subvectors, U sub f, okay? These are displacements at free DOFs, okay? And in our case, it's just U1 and U2, okay? You can see that this notation could be reserved for a general case, right? And then you have U sub D. And these are displacements at restrained DOFs. Okay, and in this case, we get U3 U4, U5, and U6. Okay. All right, and so then we can talk about a displacement vector, okay, for the entire structure, and that displacement vector would typically break up into UF and UD, right? We first number the UFs, right? Then we number the UDs. And in our case, it just becomes, right? We can separate the two. U1, U2, U3, U4, U5, U6, where the free and the restrained DOFs are separated by a dashed line like this. Okay? All right, so next, let's look at the forces. Okay, these are two elements, A and B, right? These are nodes. Again, I'm going to do an expanded view like this. Okay, this is 1, this is 2, this is 3. Okay, so each one of those guys, right, can build up internal forces. F1, right, for element A, F2 for element A, F3 for element A, F4 for element A, like this. Okay. Likewise, F1 for element B, F2 for element B, F3 for element B, and F4 for element B, like this. Okay. These are internal forces. Okay. Right. These internal forces provide equal and opposite action onto the nodes, right? So node 1 will see F1A pointing in the opposite direction, right? And F2A, okay, pointing in the opposite direction, right? Node 2 will see F3A and F3B pointing in the negative X, and F4A and F4B pointing in the negative Y. Okay. Finally, node 3 will see F1B and F2B, okay, pointing in the direction opposite to the internal force developed in the element. Okay. Right. So then, in principle, right, I can go ahead and apply external forces to my degrees of freedom. Okay. And the way I will number the external forces is in the same way as I'll number the displacements. Okay. So element node 2 can have an applied external force P1 acting this way and P2 acting this way, right? P3 acting this way, P4 acting this way, right? And then P5 acting this way, and P6 acting this way. Okay. Good. Right. And so what I can do with the apply, where the P's, right, are applied nodal forces to the structure, right? You can hang up a weight, or for example, you can have some distributed load as we studied, right? But then you have to take that distributed load and convert this to an equivalent and nodal loads. We'll study that in the future lectures, right? For now, just say, you can have these P1, P2, P3, P4, P5, P6 acting on the structure abstractly, right? Then for the nodes, in order to be in equilibrium, it has to develop the forces, right, that counteract those in the appropriate way, right? And then there'll be internal forces that will be developed in every structural member. And that's going to be sort of the force distribution. Okay? But let's go back to P's, right? Just like the displacements, we can define P sub F, okay? P sub F is P1 and P2 for this problem, okay? And this is vector of applied or external forces applied, right, forces at which DOFs? At three DOFs, right? And likewise we have PD, okay? These are the remaining guys, P3, P4, P5, and P6, okay? And this would be vector of applied forces at restrained DOFs. Okay. Right. And so now we can get a total P, and the way we think of total P is that we place PF first, like this, and then separate it from PDs. Okay. In our case, special case, this becomes P1, P2, P3, P4, P5, and P6, okay? Right, and then sort of in this linear structural analysis situation, right, what we'd like to develop, and we'll show you how, right, are relationships like this, where on the left-hand side, right, you have a matrix vector system like this at the structure level, okay, where these becomes UFs, these becomes UDs, okay, these become PFs, this becomes PDs, right, as arranged. Right, so then as a result, that partitioning of the degrees of freedom will impose for you a partitioning of the left-hand side matrix into KFF, right, the part that connects the free degrees of freedom with the corresponding forces, KFD, right, free forces with restrained degrees of freedom, KDF, okay, vice versa, and then KDD, okay, the K that connects the restrained degrees of freedom and the corresponding forces. And so the left-hand side becomes K, or the structure stiffness matrix. Okay, and then we'll look at the K separately. Okay, and so what's often of interest, right, as you can see, if UD is 0, okay, the degrees of freedom are truly restrained, okay, then KFD doesn't really matter, okay, because it'll multiply 0 vector anyway. And then the structural system reduces to KFF, UF equals to PF, like this. Okay, and so in the next lecture, we'll take a look at how to derive KFF. So sometimes this is referred to as the reduced structural stiffness matrix. Okay, let me stop here.